Welcome and thank you for joining us here on Stream 3 at DSC Europe 25. My name is Milica and I'll be your host for this session. We're kicking things off with Maria Peterberg, SW AI Team Leader at Intel Corporation. Her session is titled Peer Direct on Gaudi, enabling host NIC communication for distributed AI training without losing performance. Maria, the stage is yours.
Thank you so much. And thank you, DSC, for having me.
Hello, Dmitry. Can you hear me?
Hi.
Yeah. I can hear.
It's okay.
So I think we should start now. Okay. So first of all, thank you, DSC, for having me. I know this was supposed to be a face-to-face session because it's not the usual hands-on session you have online. But since I have a newborn, I asked kindly to have it online, and you included me. So thank you for that. And so yes, let's begin. Hi, everyone, and thank you so much for joining me today. Before we start, just a few words about myself. So my name is Maria, and I've been in the tech industry for over a decade now. My passion for artificial intelligence actually began back in my uni years, long before AI was what it is today. And it has shaped the entire trajectory of my career. So actually, for the past 5 years, I had the privilege to work exclusively in the deep learning domain, focusing on the lower level layers of training, where hardware, memory, and performance truly define what system can achieve. I started my days in Intel's Habana Labs as lead engineer and HCCL team, and I was working on the communication library that enables Gaudi accelerators, which is what we develop to scale efficiently. It's very similar to what Nickel does for NVIDIA. These days, I lead the runtime team that's responsible for everything that happens during runtime of model training on Gaudi. It means handling synchronization, graph execution, hardware resource management, scheduling, and so on and so forth. And so today, I'm excited to take you behind the scenes into this world, the systems, the challenges, the insights, and the innovations that really power distributed AI training today. So what's on the agenda today? I think, as many of you already know, in large-scale distributed training, every microsecond counts. And in this session, I'll walk you through how I enabled hostNIC-based communication on AWS Gaudi clusters while still achieving near-native performance through an aggressive optimization known as Peer Direct. We'll break down all the architecture behind Gaudi accelerators. We'll explore how RDMA pathways eliminate traditional CPU bottlenecks, and discuss what it really takes to balance flexibility, scalability, and throughput in production training environments. Except deep technical insights, of course, and architectural diagrams, we will dive into the hardcore implementation details. But we'll start with a quick refresher of key concepts, so it will help us to frame the rest of the talk. We will talk about what deep learning actually means, what is Gaudi, and what makes it unique compared to other hardware in today's AI landscape. What are hostNICs, and how they're different from Gaudi NICs, how communication libraries operate across clusters, what collective operation is and why they matter, and so much more. So I hope you're ready, energized, and curious, because we're about to go on a very fun and technical journey. And I'm going to start right now. As I said, before we dive deeper into distributed training and performance challenges, let's quickly recap on what deep learning actually means and what it actually is. So deep learning is a branch of machine learning that uses artificial neural networks. These are computational models inspired by the human brain. These networks are made up of layers of interconnected neurons. And the deeper the network, the most complex the pattern it can learn. What makes deep learning powerful is actually that it learns from examples. Instead of manually coding rules, we feed the network large amounts of data, and it automatically learns the important features. This is called automatic feature extraction. and it's one of the key reasons deep learning has taken over fields like vision and speech and natural language. Another very important thing to know is that deep learning scales extremely well. The more data and compute you give it, the better it gets. These networks thrive when we can train them at massive scale with high throughput, low latency communication between devices. Now that we understand the basics of deep learning, let's look at the computations that actually dominate training. What's interesting to notice is that despite all of the complexity of modern models, most of the compute still boils down to just a few fundamental operations. The first one, and far the largest, is matrix multiplication. This accounts to 70% to 90% of the workload in both forward and backward passes. If you ever wondered why accelerators like to optimize gems so heavily, that's the reason. Next, for models dealing with images or video, we have convolutions, typically around 5 to 15%. These extract spatial features, edges, textures, and patterns. In modern architectures, especially transformers, we see a similar compute footprint for attention mechanisms, again, around 5 to 15%. Attention helps the model focus on the most relevant part of the input. Then we have two categories that barely register on the compute chart: activation functions and normalization layers, each typically under 2%. They're light on compute, but extremely important. Activation provides nonlinearity. Otherwise, your network is just a giant linear function, while normalization stabilizes training and speeds up convergence. Here you can actually see the breakdown visually. The big ring dominating the chart, that's the matrix multiplication. This is where the 70 to 90% of the compute happens in modern deep learning models. Then you can see much smaller slices for convolutions and attention mechanisms, each roughly, as I mentioned, 5 to 15% depending on the architecture. And the tiny purple area labeled others, that's everything else: activations, normalizations, reshapes, softmax, and so on and so forth. So all of these combined barely move the needle compared to the heavy matrix math. Now that we understand what deep learning workloads look like, the next question should naturally be, what hardware actually runs all this? And today we have several categories of compute devices, each with its own strengths and trade-offs. So let's walk through them quickly. CPUs are the most flexible. They're fantastic for pre-processing, orchestration, and running the surrounding application logic. But when it comes to large-scale training, they're simply too slow. GPUs are the workhorses. Most people know about them. They're massively parallel, have a very mature machine learning software stack, such as CUDA, and can handle a wide variety of workloads. But their drawbacks? Higher power consumption, and the fact that GPUs weren't originally designed specifically for deep learning. CPUs, on the other hand, were designed for deep learning. They were designed for optimized tensor operations, given extremely high throughput. But they're largely tied to Google Cloud, and so less flexible for general tasks. And then we have the custom AI accelerators. This is where Gaudi sits. These devices are built from the ground up for deep learning. High memory bandwidth, optimized interconnects, low latency communication. But the trade-off is a smaller software ecosystem. And finally, FPGAs. They're reconfigurable and extremely energy efficient for specialized workloads, but harder to program and really not ideal for today's giant models. So I guess the bottom line is, no single device is perfect. They all have advantages and drawbacks. So let's talk about what Gaudi actually is. Gaudi is a specialized AI processor, like I mentioned. It's purpose-built by Habana Labs, my company, which became part of Intel in 2019. Gaudi was designed specifically to train deep learning models at large scale. Unlike GPUs, which were originally designed for graphics and then adapted for AI, Gaudi was designed from day one for deep learning. Its architecture, its interconnect, its memory system. Everything is optimized for the kinds of data flows we just talked about, massive matrix multiplications and tensor operations. This makes Gaudi a strong alternative to the dominant GPU-based training systems from NVIDIA. The key point here is that Gaudi is not a general-purpose chip that happens to run training well. It is a purpose-built accelerator. It was tuned specifically for patterns and bottlenecks of modern AI workloads. To understand PeerDirect, which is the main feature I'm going to discuss today, we first need to go and understand what RDMA, that stands for Remote Direct Memory Access, actually is. So RDMA is a communication technology that allows one machine to directly read or write to the memory of another machine without involving either CPU or operating system. That means no context switches, no kernel overhead, no CPU scheduling delays. Just a pure direct memory-to-memory transfer over the network. And this is incredibly important for deep learning, because once you get to multi-node training, communication becomes one of the biggest bottlenecks. Bypassing the CPU and operating system entirely enables lower latency, higher throughput, and much more predictable performance. In other words, RDMA is the foundation that enables the fastest form of distributed communication, and Gaudi builds directly on top of it. To understand why RDMA is so powerful, let's compare it to something we all know, traditional TCP/IP networking. In traditional networking, sending data involves a lot of steps and a lot of overhead. The data starts in user space, then gets copied into kernel space, then copied again into the network interface card, the NIC. Then it travels over the network, and on the receiving side, everything happens again. NIC buffer, then kernel, then user space. Every one of those steps comes with CPU context switches, kernel calls, and multiple memory copies. So you're not just sending the data, you're copying it and moving it around over again and again before it ever arrives where it's needed. RDMA eliminates all that. With RDMA, the data path becomes extremely simple. From the sender's memory directly to the receiver's memory. No CPU involvement, no kernel calls, no buffer copies. This is why RDMA gives dramatically lower latency and higher bandwidth. It cuts out all the middlemen. And this streamlined data path is exactly what makes it so ideal for distributed deep learning. Now that we understand the core idea behind RDMA, let's quickly walk through the key properties that make it so powerful, especially, as I mentioned, for distributed deep training. So it has zero copy. This is one of the biggest wins. As I mentioned, RDMA lets data move directly from one device memory to another using DMA, direct memory access. No extra copies along the way. This cuts out all the overhead and saves a ton of CPU cycles. It also has a kernel bypass. With RDMA, the operating system is not involved during the actual transfer. This is one of the reasons RDMA is so fast. Low latency. When you remove CPU involvement and kernel overhead, latency naturally drops. And in distributed training, latency is everything, especially for operations like all reduce that sit in the critical path. I will explain later what these operations actually mean, of course. High throughput. Since the CPU isn't the bottleneck anymore, you can push data through the NIC at extremely high rates. It also uses QPs. RDMA communications is controlled by QPs. It's queue pairs consisting of send queue and receive queue. These allow for a very granular, reliable, hardware-controlled data transfer. And finally, RDMA is enabled by smart NICs, like the ones in Gaudi systems. These NICs know how to perform RDMA operations directly in hardware, offloading the whole data moving process from the CPU. So when you put all these pieces together, the zero copy, the kernel bypass, the low latency, and hardware accelerated transfers, you get a communication technology that is perfectly suited for large-scale, high-throughput deep learning. Now, let's look at how Gaudi actually uses RDMA in its architecture. Gaudi relies on RDMA via RoCE v2, RDMA over Converged Ethernet, as its primary interconnect for communication between chips. This applies whether the chips are on the same node or distributed across nodes. In simpler words, Gaudi's chips talk to each other directly over the high-speed RDMA link, without CPU ever being involved. In Gaudi processor, each one includes 24 built-in RDMA NICs, while each one is running at 100 gigabits per second. For Gaudi 3, for instance, which is the newer one, these 24 NICs are at 200 gigabits per second, doubling the bandwidth. And notice, these NICs are built directly into the silicon. There are no external network cards, no extra hardware to manage. Everything is tightly integrated for maximum performance. All these NICs together form a fabric of point-to-point direct links between Gaudi processors, giving us extremely efficient, fast chip-to-chip communication. Now, let's talk about HCCL, the team I was part of. It's also pronounced as HICL. It's easier like that, so I'll probably pronounce it like that. It stands for the Habana Collective Communication Library. And if you worked with NVIDIA's GPUs, you're probably familiar with the NICL, NVIDIA's Collective Communication Library. HICL is basically Habana's equivalent. It's a high-performance communication library developed specifically for Gaudi accelerators. Its entire purpose is to make distributed deep learning training fast and efficient. HICL provides highly optimized implementations for the core collective communication primitives that modern training depends on, such as all-reduce that I mentioned before, all-gather, reduce-scatter, and others. These operations are the glue of distributed training. They synchronize guardians, share model parameters, and keep devices aligned. Whether you train a model across multiple devices or multiple nodes, whether you're using data parallelism or model parallelism, HICL is the layer making sure everything stays in sync, and does so with minimal overhead. So in short, HICL is what enables Gaudi to scale from one chip to an entire cluster efficiently and reliably. And so as promised, before we get deeper into performance, let's talk about these collective operations and understand what they mean, because these are the backbone of distributed deep learning training. Collective communications are communication patterns where every device participates. They can be symmetrical, where all workers perform the same type of communication at the same time, or asymmetrical. What's important is that collectives aren't defined by a single implementation. They can be built using different algorithms, ring-based, tree-based, recursive doubling, each optimized for different aspects like latency or throughput. And the origin of all this comes from MPI, the message passing interface, which has been the gold standard for collective communication for decades. Examples of such collective algorithms include all-reduce. That operation combines values from all workers, reduces them into one result, like sum or average, and then distributes that result back to every worker. Another example would be all-gather, where each device shares its tensor and receives everyone else's. Reduce-scatter, for instance, first reduces the data and then distributed different chunks to different ranks. And broadcast, that's where one node sends all other nodes his information. Now, let's look into how Gaudi chips actually communicate with each other during training. In this example, we have 8 Gaudi processors. Each Gaudi processor comes with 10 high-speed network ports, and these ports can be connected directly using copper or optical cables, or through switches for larger topologies. Here's what the communication flow looks like. Training runs using data parallelism, meaning each Gaudi processes a different slice of the input batch. After each forward and backward pass, every Gaudi chip computes its own guardians. But for the model to stay consistent, these guardians must be aggregated across all devices. This is where collective operations like all-reduce come in. The HICL library handles this entire process. It orchestrates which device sends what, to whom, and when, in the most optimal algorithm. Under the hood, Gaudi devices communicate using the RDMA over RoCE v2. They write directly into each other's memory regions using RDMA write or RDMA read. So essentially, Gaudi chips synchronize Guardians at very high speed with minimal overhead and without wasting CPU cycles. So why HICL exists and why it's such a critical component of Gaudi's training performance? As discussed, modern AI training isn't done on a single device anymore. Models today run across 8, 64, and in some cases, thousands and thousands of accelerators at once. And once you scale out like this, communication becomes just as important as compute. During training, devices constantly need to talk to each other using the collective operations I mentioned earlier. These operations must be fast, synchronized, and highly scalable. If they are not, everything breaks. You get high latency, network congestion, and your accelerators sit idle instead of training. If we use native point-to-point send-receive patterns, we'd immediately run into high latency, network bottlenecks, and ultimately poor hardware utilization. So instead, HICL takes over. And this is where it becomes powerful. It uses optimized collective algorithms. It leverages RDMA over RoCE v2. It exploits Gaudi built-in NICs, giving full bandwidth directly from the chip. And it has topology awareness, meaning it understands the physical layout of the devices and routes communication in the most efficient way possible. So in other words, HICL ensures that as your model scales, your communication scales with it, without slowing the system down. That's the difference between a system that trains smoothly and one that chokes on its own networking. Now, let's shift our attention to the role of the host NIC, because this is where the real-world challenges begin to appear. A host NIC is simply the standard network card on the server, usually something like Intel, Broadcom, or Mellanox PCIe card. These NICs are connected directly to the host CPU and to its main memory. Of course, this creates several limitations. First, these NICs may or may not support RDMA, and in most cases, they are not. Second, they're designed for general purpose networking, like web traffic, storage, SSH, and not high-speed accelerator-to-accelerator communication. Even so, when we introduced Gaudi, which has its own built-in, on-die RDMA NICs, some clients resisted using our suggested way of communication. And why so? Because using Gaudi's built-in NICs meant they needed to change their data center network topology. They had to buy new switches, new cables, adjust routing, and all of that costs money and time. Some customers simply weren't willing to restructure their entire network just to adapt to a new accelerator. So instead of embracing the Gaudi NICs, which are incredibly powerful, they opted to stick with their existing host NICs. But of course, this meant they couldn't fully benefit from the low latency, high bandwidth RDMA pathways that Gaudi was built around. And this gap between customer infrastructure and the Gaudi architecture is exactly the challenge that PureDirect was designed to solve. To understand the problem better, we first need to understand the data flow. Here's what actually happens when communication goes through the host NIC instead of Gaudi native RDMA path. So it starts by Gaudi copying the data from the HBM, its high bandwidth on-chip memory, into the host buffer. The host CPU now has to wake up and pick up the data. The CPU hands it off to the host NIC, which then sends it over the network using traditional protocol like TCP/IP, for instance. On the remote machine, the host NIC receives the packet and the CPU writes it into memory. Finally, the data must be copied back from the host DRAM into the remote Gaudi HBM. So instead of a clean, direct device-to-device transfer, we involve the host CPU, host DRAM, PCIe transfer, and hostnic on both sides. All of these steps introduce extra copies, extra context switches, and bottlenecks. The result is, of course, high latency and significantly lower bandwidth compared to Gaudi's built-in RDMA engines. Now, let's look at a real-world example where all this becomes very relevant. Amazon's DL1 instance, which was the first cloud instance ever to use Gaudi accelerators instead of NVIDIA's GPUs. DL1 was designed specifically for deep learning training, a cost-effective alternative for large-scale AI workloads. But there was one major constraint. Instead of using Gaudi built-in high-speed NICs, Amazon required the instance to rely on host NICs. Why? Because integrating Gaudi's own NICs into AWS existing data center topology would have required physical infrastructure changes, new switches, new wiring, and more complex bring-up. So AWS chose the simpler path, route all traffic through the host. And this decision had consequences, of course. When Gaudi was deployed on DL1, we immediately noticed a large performance gap when scaling out. The communication path throughput, the hostnic introduced higher latency and lower bandwidth, enough to cause a huge performance degradation in real training workloads. So even though DL1 was an exciting milestone for Gaudi, this network bottleneck slowed down adoption and created a very real challenge that needed to be solved immediately. Now, before we continue, we need to stop and ask ourselves, why performance matters so much in large-scale AI training, especially today? Modern foundation models like GPT-5, Palm, and DALL-E, and the next generation of LLMs require weeks or even months of training. So that's even when you're training on thousands of accelerators, and every percentage point of performance you gain really matters. Let's break down some examples as to why performance is crucial. Time to market, for instance, is fundamentally dictated by performance. The faster we can train, iterate, and validate ideas, the faster models reach production. Faster performance directly translates to quicker iteration, where teams can run more experiments, debug faster, and retrain models without waiting weeks. Researchers can validate new ideas more often, which is critical in this rapidly evolving field. And this one is huge. Companies like OpenAI, Google, and Anthropic, they're in a race. Whoever trains and deploys first has a real competitive advantage. To put this into perspective, if you take a training job that normally requires 30 days, and through better optimization, bring it down to 10, you triple the number of experiments you can run in the same time. And in AI research, more experiments means faster breakthroughs. Another reason performance is so crucial is, of course, cost. When you train large models, you're not running on a laptop. You're renting or operating massive compute clusters, sometimes thousands of accelerators at once. And at that scale, performance directly translates to money. If each training iteration takes twice as long, the user is literally burning twice the money. Because there is no magic. The cloud providers, they charge per hour, and the meters keep running. On AWS, Azure, or internal clusters, a single full training run for a modern LLM can cost millions of dollars. So even a small improvement, say a 10% performance uplift, can save millions per year. And that's why companies obsess over every microsecond of communication and every % of utilization. Another major reason performance matters is hardware utilization. Poor communication performance doesn't just slow things down. It leads to underutilized hardware. And underutilized hardware is the most expensive thing you can have in a modern AI cluster. When a user trains a model, the accelerators might stall because of slow or insufficient collective communication, I/O bottlenecks in the data pipeline, or limited memory bandwidth. And when that happens, the user is wasting compute capacity as accelerators just sit idle. power, which is a massive cost at scale, and money, since they're paying for hardware that isn't actually doing any work. With today's clusters, especially for training LLMs, keeping above 90% utilization is absolutely crucial. Every percentage below that is literally paying for idle silicon, and at that scale, that becomes millions. Another challenge that affects absolutely everything in distributed training is the model size. We all know models are getting bigger, but what's interesting is that training time is growing even faster than model size itself. And the reason is simple. As models scale, the requirements around them scale even faster, especially in 3 areas: computation, communication, and memory. So if we want to keep up the hardware and the software stack, they must evolve together. First, we need high bandwidth memory and HBM just to feed these models quickly enough. Second, we need efficient interconnects. This is where technologies like RDMA come in. Without fast-to-fast device-to-device communication, accelerators spend most of their time waiting instead of training. And finally, none of this matters if the software stack isn't scale. Libraries like HICL and NICL DeepSpeed, they have to orchestrate communication across dozens, hundreds, and thousands of devices without collapsing under the synchronization overhead. The bottom line is simple. Without strong performance at every layer, large-scale model training becomes infeasible. And lastly, let's shift to a dimension that's becoming impossible to ignore: the environmental cost of large-scale AI training. Training GPT-3 alone reportedly consumed over 1 gigawatt hour of electricity. That's a substantial amount, enough to power hundreds of homes for an entire year. And while we don't have the official numbers for GPT-4 or GPT-5, we can safely assume the energy footprint has only grown. This is where performance matters far beyond speed or cost. Better performance directly translates to less compute time, lower energy consumption, and smaller carbon footprint. So every % of efficiency we recover isn't just about saving money, it's about making AI more sustainable. And as more companies publicly commit to green AI practices, performance optimizations, such as PeerDirect, becomes essential. They're no longer nice to have features. They're part of reducing the environmental impact of massive training runs. So, now that we understand the immense importance of performance in large-scale deep learning training, let's go back to the enormous challenge we faced with Amazon. One of our biggest customers rejected Gaudi's integrated NICs and chose to proceed only with host NICs, a decision that immediately crippled performance at scale. The solution had to be designed, implemented, and deployed at record speed, flawlessly integrate with a highly complex software stack, and deliver a significant performance uplift. There was no margin for error. It was a technically demanding, time-sensitive challenge that the stakes could not have been higher. At this point, we had to think creatively. If Amazon wasn't going to use Gaudi built-in high-performance NICs, we needed another path, one that could still deliver near-native performance at scale. This is where EFA, the Elastic Fabric Adapter, came into the picture. I collaborated with AWS teams to integrate the EFA support into the Habana software stack and enable the PeerDirect communication. This was a major architectural shift, essentially building a new communication path tailored especially for Gaudi running in the AWS ecosystem. So, what is EFA? Essentially, EFA is AWS's high-performance network interface. It's designed for demanding workloads like HPC or distributed AI training. It provides exactly the kind of capabilities we need: low latency, high bandwidth, OS bypass, and so more. Let's take a closer look at EFA's capabilities. EFA brings several critical features that make it suitable for high-performance training. First, the throughput. EFA supports up to 100 gigabits per second, enabling fast data movement between EC2 instances. EFA also integrates seamlessly with Leaf Fabric, a user space API designed specifically for high-performance communication. Next, we have the kernel bypass. Applications can communicate directly with the network hardware through Leaf Fabric, avoiding expensive OS involvement and significantly reducing overhead. EFA also delivers low latency, typically under 10 microseconds, putting it in the same class as InfiniBand. It provides RDMA-like semantics, enabling zero-copy communication and efficient one-sided operations like send, receive, write, or read. And finally, today, once the support had already been done, it's also optimized for AI workloads with built-in support for MPI, HICL, and NICL libraries, which is essential because deep learning frameworks rely heavily on these libraries. Together, these capabilities make EFA a strong fit for scaling distributed deep learning on AWS. A moment ago, I mentioned that EFA integrates with Leaf Fabric, and we should stop and deep dive a bit more into what Leaf Fabric is. Leaf Fabric is a high-performance communication library built specifically for demanding workloads like HPC clusters or large-scale training. It sits at the heart of the Open Fabrics interfaces, the OFI framework, which provides a unified, scalable API over multiple low-level networking technologies. Instead of writing different code for Rocky, for InfiniBand, for EFA, for TCP, Leaf Fabric exposes single consistent interface that abstracts these hardware differences away. This makes Leaf Fabric the foundation for high-performance communication stacks, and the reason why libraries like NICL and HICL can efficiently run over different hardware backends. Now we should talk about the OFI wrapper. This is a key software bridge that lets HICL run seamlessly over industry-standard hosting through the API of Leaf Fabric. What makes it powerful is that it provides dynamic linkage between the Leaf Fabric library and HICL. It allows HICL to remain completely decoupled from Leaf Fabric's internals, avoiding any direct source code dependencies and keeping the library fully agnostic to the underlying communication provider. HICL does not need to know anything about EFA or any other underlying providers such as Verbs or TCP. It simply issues a collective operation and the OFI wrapper translates it into the correct Leaf Fabric call. This lets HICL run collective communication over Verbs, EFA, or any Leaf Fabric compatible provider, which still maintaining the performance, guarantees, and communication semantics expected from the Gaudi stack, and without polluting HICL's code base with Leaf Fabric specific logic. By the way, the implementation is open source and available at the link I just posted. And now we arrive at the most critical part of the entire solution, the PeerDirect feature itself, a capability that only becomes possible when built on top of Leaf Fabric and AWS EFA. So PeerDirect is the mechanism that makes the impossible possible. It allows Gaudi accelerators to exchange data directly and efficiently, even when the hardware topology works against us. By bypassing host memory and tapping into Leaf Fabric RDMA, it preserves high-performance communication without relying on Gaudi's integrated NICs or standard RDMA infrastructure. In other words, PeerDirect gives us RDMA capabilities where no RDMA should even exist. So how does this magic happen? How does PeerDirect actually work under the hood? Let me first walk you through the software architecture we designed on a high level, a joint effort across HICL Linux driver team and Leaf Fabric engineers to make true device-to-device RDMA possible. First, everything begins with memory registration. HICL instructs Leaf Fabric to register memory regions directly inside Gaudi HBMs. Without this step, RDMA simply cannot work. You cannot transfer data you haven't registered. Next, Leaf Fabric set up what's called queue pairs, or QPs, between the source and the destination Gaudis. This is the communication channel where all RDMA messages flow. Once the QPs are created, both sides exchange the remote keys, or R keys, and the virtual addresses associated with the HBM buffers. Think of it as agreeing on the exact memory coordinates where data will be written or read. Now the magic starts. When HICL initiates the transfer, the source Gaudi performs an RDMA write directly from its HBM into the destination Gaudi's HBM, using the LibFabric memory handles we just registered. There is no CPU involvement, no host memory bounces. It's true device-to-device communication over the network fabric. Finally, once the transfer is complete, LibFabric signals completion through a completion queue. HICL receives that signal and immediately continues its computation pipeline using the newly received data. No polling loops, no unnecessary synchronization overhead, just fast, efficient peer-to-peer transfers. Now let's dive deeper into the 3 core features that make this entire system possible. Memory region registration with LKD, that stands for Linux kernel driver, memory region registration with LibFabric, and of course, managing a cache. Let's start with the first one and discuss how the way memory regions are registered with Habana's Linux kernel driver. So when HICL wants to send or receive data directly from HBM via RDMA, the first step is to register that specific HBM region with the NIC. In our implementation, this is done through Habana's kernel-side API, which takes an address and size and returns a DMA buff file descriptor. This file descriptor is the kernel's way of exporting that HBM region in a form that the NIC can legally and safely access. From here on, the NIC and the libraries can treat this memory just like any RDMA-capable device memory. HICL then stores this file descriptor in an internal LRU cache as a mapping from address and size to file descriptor, so repeated operations over the same region do not require re-registration. This caching is critical for performance because memory registration is one of the most expansive operations in RDMA workloads. Once the memory is exported from the kernel as a DMA buff file descriptor, we still need to make it usable for RDMA operations inside LibFabric. This is where the second stage of the registration happens. HICL calls VMR regattr, passing the DMA buff file descriptor, the buffer address, and the size. This step essentially tells LibFabric, hey, here's a memory region that came from the kernel. Please create an RDMA-capable memory handle for it. LibFabric then associates that file descriptor with the LibFabric memory region object, called VMR. This handle is what EFA will actually use when performing RDMA writes and reads. At this point, our registration cache entirely becomes fully populated. It has address and size to file descriptor and LibFabric handle. This completes the memory registration pipeline across all layers, kernel, DMA buff, and LibFabric, making the region ready for peer direct transfers. As I walked through the registration path, I mentioned a DMA buff file descriptor, almost in a passing. But this object sits at the heart of every cross-device data transfer in Linux. So let's take just a moment to unpack what DMA buff actually is and why it's essential. DMA buff is a standard Linux kernel mechanism that allows different device drivers to share buffers with each other. It was originally designed for GPUs and display drivers, but in our case, it became a key building block for enabling true Gaudi to Gaudi peer-to-peer transfers. And so how does that work? First, a buffer is allocated by one driver, the exporter. This is typically Gaudi's kernel driver, allocating memory inside HBM. The exporter then publishes that buffer as a DMA buff object. This object can be associated with a file descriptor, which can be passed up to user space and then down to another driver. The receiver driver, the importer, takes that file descriptor and resolves it back into the DMA buff object. The importer then performs address translation, so it knows where this buffer lives physically on the device. Once mapping is completed, the importer knows the buffer's DMA address. And with that address, the peer device can now issue real peer-to-peer DMA transactions directly to that buffer. No CPU, no host memory bounds, no copy. So DMA buff is the kernel-level foundation that allows two Gaudi's accelerators to see each other's HBM buffers. And now let's go back to the cache. I already briefly mentioned that we implemented an LRU cache, but this component deserves its own spotlight because it plays a crucial role in keeping the entire registration flow efficient. So when HICL needs to register a memory region with RDMA, that process is actually quite expensive. It requires exporting the DMA buff from Linux kernel driver and then registering it again inside LibFabric to obtain the memory handle. If we repeated this full process for every tensor, every iteration, training would slow down dramatically. So instead, we implemented a memory map regions cache, essentially an LRU cache that maps the address and size to the file descriptor and the LibFabric handle. Here's how it works. Whenever HICL needs to register a region, it first consults the cache. It checks whether this exact memory region, defined by its address and size, already exists. If there's a cache hit, we skip both expensive steps. No new DMA buff export, no new LibFabric registration. Instead, we simply reuse the existing LibFabric memory handle, and this alone saves us a tremendous amount of overhead during training. If the entry is not found, then we fall back to performing the full registration flow, first through LKD, then through LibFabric. And once we obtain the result, we insert the new entry into the cache. Finally, when the cache becomes full, we evict the least recently used entry and properly deregister it to keep everything safe and clean. This LRU mechanism dramatically reduces the number of memory registration operations we have to perform, which directly reduces latency and improves overall throughput of collective operations. It's a small subsystem, but it has a massive impact on the end-to-end performance. Now that we understand how the LRU cache is built and maintained, let's look at what happens during the common case, when HICL needs to transfer data from a memory region that was already registered earlier. This is where all the work we did really pays off. The first step is a cache lookup. HICL computes the key, which is simply the address and size, and checks if this entry exists in the memory map regions cache. If it's a hit, then we already have the file descriptor exported earlier from the LKD and the LibFabric memory handle that we previously registered. Both of these are immediately available without doing any new work. That brings us to step 2, skipping registration entirely. We don't call LKD, we don't call LibFabric, we don't touch the DMA buff or anything at all. It's literally zero overhead. Then step 3, the actual RDMA transfer. HICL simply takes the cached LibFabric memory handle and uses it directly in the RDMA operation. No repeated setup, no repeated translation, just pure fast path execution. And the transfer flow exactly through the stack we built. HICL to the OFI wrapper, to the LibFabric, to the RDMA library, to the RDMA driver, and then to the NIC. All the expensive registration logic is avoided, and the system behaves as if the NIC already knows every buffer, which is exactly the illusion the cache is designed to create. Now that we walked through the slow path, the fast path, and the role of the cache, let me tie all of these together with a complete architectural overview of how memory registration actually flows through the system. So what you're seeing here is the full end-to-end data path, from HICL at the top all the way down to the NIC at the bottom. Let's start off the left with HICL. When HICL needs to make a Gaudi HBM buffer accessible for RDMA, the very first step is to interact with the Linux kernel driver using the custom API. This exports a DMA buff file descriptor representing that HBM region. At this point, HICL stores a partial cache entry, an address and a size, to a file descriptor. Next, we move to the right side of the diagram, libfabric. It's marked in blue. HICL provides that file descriptor to libfabric by calling the FMR reg attr, which effectively tells libfabric, here's a DMA buff file descriptor. Please turn this into an RDMA-capable memory region. libfabric then interacts with the RDMA library and the RDMA driver, which ultimately programs the hardware NIC. When this registration completes, libfabric returns a memory region handle. This is the critical piece HICL needs to perform RDMA operations. Now HICL updates the cache entry to its final form, an address and size, to a file descriptor and a libfabric handle. From this point on, any subsequent transfer involving the same buffer completely bypasses all the logic on the left and right. There is no need to re-export DMA buff, no need to re-register, no need to touch the kernel again. HICL immediately retrieves file descriptor and libfabric handle from the cache and uses them directly. Now let's walk through what actually happens during a real write operation, when one Gaudi device in box 0 wants to write directly into the HBM of another Gaudi in box 1. This slide ties together everything we've discussed so far. Memory registration, DMA buff, libfabric, the LRU cache, and finally, peer direct itself. So let's begin. The write operation begins on box 0. That's the gray box on the left. Gaudi 0 initiates a write request. The very first thing HICL does is to check whether the target memory region of the remote Gaudi is already registered. This check goes straight into the memory mapped region's LRU cache inside HICL. If the region is found, meaning we already have both the DMA buff file descriptor and the libfabric memory handle, and HICL immediately returns the cached handle. This is the fast path, with 0 registration cost. If it's not found, then we trigger the full registration flow we went through in earlier slides. That involves exporting the DMA buff and registering it with libfabric. Once completed, the new file descriptor and libfabric handle is saved back to the cache. Next, to issuing the RDMA write. Once HICL has the libfabric memory handle, either from cache or from fresh registration, the actual write operation begins. The write request flows down through the layers. HICL to the OFI wrapper, to libfabric, to RDMA library, to RDMA driver, and finally to the EFA NIC. Each layer contributes a piece of the translation, from high-level collective semantics all the way down to the NIC level. The packet is then transmitted across the elastic fabric adapter, the EFA connection, between the two servers. Just a reminder, this is AWS's optimized low latency, high throughput networking layer for multi-node distributed training. Now, the most important part. What makes peer direct so special is the direct write into the remote Gaudi HBM on box 1. The remote EFA NIC already knows how to access the mapped HBM region. This is no bound through host memory, no staging buffer, no CPU involvement. Thanks to DMA buff and libfabric registration, the NIC can directly DMA the packet into the target Gaudi 8's HBM region. This is true device-to-device RDMA across machines. So the final result is that Gaudi 0 writes directly into Gaudi 8's HBM with minimal latency and maximum bandwidth. HICL never copies data through the host. Okay, so we just covered a lot of flow level magic. If your brain feels like a mush, that's completely normal. It means you understood everything perfectly. So I think we can all take a deep breath, since that was the deepest, most low level part of the presentation. And by the way, That is actually my dog on a trip to Paris. So, now that we walked through the architecture and fully unpacked the technical details behind our solution, let me take you behind the scenes into the actual experience building this product, and most importantly, the achievements that came out of it. Because getting PeerDirect to work was not an easy engineering task. It was a journey, and it was anything but straightforward. At the time, LeafFabric was still an emerging, barely adopted technology, especially in the AI accelerator space. Public information was almost non-existent. Documentation was thin. Examples were rare, and community discussions were basically silent. This meant that many critical design, debugging, and integration decisions had to be made from first principles, diving directly into LeafFabric's source code, tracing execution paths, and understanding its internal behavior to make it work for Gaudi. Another major challenge came from the human side of the project. To deliver PeerDirect, we had to work extremely closely with AWS engineers, who were obviously in a completely opposite time zone, essentially making our collaboration a continuous relay race. This meant that rapid iteration and real-time debugging was almost impossible. Every question, every log, every hypothesis often required a 24-hour turnaround. So a single bug could easily cost 2 to 3 days, adding enormous pressure on already aggressive deadlines. Another challenge came from the stakes. This wasn't a nice-to-have feature. It was a blocker. So every bug fix, every design choice, every performance registration carried enormous urgency. And to make things even more interesting, no one at Habana Labs had deep experience with LeafFabric internals at that time. So I found myself debugging extremely low-level LeafFabric code day and night. Provider logic, RDMA memory registration flows, completion semantics, and whatnot. All while simultaneously designing the abstraction layer to integrate it cleanly with HICL. Many parts of LeafFabric's behavior weren't even documented anywhere, and I had to literally reverse engineer how specific providers behaved under different RDMA paths and understand how EFA deviated from traditional RDMA. This was a code base and an ecosystem that were completely unfamiliar to us. And we had to complete this under the most aggressive timelines we've worked with. But let's now talk about the innovation itself. What made this solution not just functional, but strategic for Habana and for AWS. The first major innovation was the memory regions caching mechanism. It wasn't just a small optimization, it fundamentally changed the cost of performing RDMA transfers. By tightly integrating the cache with LeafFabric, we eliminated repeater kernel registrations and turned a very expensive operation into an almost free one during runtime. This contributed directly to higher throughput and lower latency across Gaudi devices. Secondly, the entire PeerDirect path designed to be fabric agnostic. This means this isn't tied to EFA specifically. Tomorrow, if another interconnect appears, HICL's high-level logic does not need to change, thanks to the abstraction layer that future-proofs the system and allows rapid expansion to other fabrics. And finally, it enabled true accelerator-to-accelerator data movement across nodes with minimal CPU involvement where Gaudi NICs could not be used. This was the core breakthrough. Bypassing host memory, bypassing the CPU, and letting Gaudi devices ultimately communicate directly and reduce latency, increase efficiency, and ultimately enabled the large-scale deep learning workloads to run at high performance. So in short, it wasn't a feature. It was a foundation that accelerators today prepared for whatever networking technologies came next. Now let us discuss the impact, because this was a business-critical enabler. PeerDirect became a critical pillar of Gaudi's performance on AWS DL1. From day one, customers running large-scale distributed training depended on this capability to achieve efficient scaling. Without PeerDirect, Gaudi's networking performance on DL1 simply wouldn't have met the bar. This work also pushed the boundaries of what was possible with the networking technologies available at the time. But the long-term impact is even more meaningful. PeerDirect laid the architectural foundation for future high-performance communication features in Habana's stack. The abstraction, the fabric-agnostic design, and the memory registration framework all became building blocks for future scalability and next-generation network algorithms and integrations. In other words, it wasn't just solving a problem for DL1. It reshaped how Gaudi communicates across nodes and set the direction for Habana's high-performance distributed training strategy going forward. And now finally, you're probably asking yourselves, after all this effort, all this engineering, all these moving pieces, what did we actually gain? What was the payoff for all this work? Well, this is where the story gets interesting. Running with EFA PeerDirect doesn't just improve performance. It unleashes a dramatic 1.5 to 2 times acceleration across collective operations and 32 megabyte sizes. This eliminates the costly detour through host memory. Every transfer becomes leaner, faster, and far more efficient. The single architecture breakthrough removes a fundamental bottleneck in distributed training. The exact speedup varies on model and framework, of course, but the pattern is unmistakable. We have less overhead, more bandwidth, faster scaling. A breakthrough that materially elevates Gaudi's training performance on AWS. Now let's take all the architecture, all the engineering effort, all the debugging marathons, and translate it into the only thing that ultimately matters in high-performance computing, which is numbers, real numbers. This table shows the performance of HICL Collective on 32 Gaudi cards. That's 41 instances, running with and without the EFA PeerDirect. Let me walk you through it. All reduce operation with PeerDirect has a 154% improvement, a massive leap for one of the most bandwidth-intensive collectives in deep learning. Altogether has a 202% improvement. Yes, double the throughput. This is the kind of jump you almost never see without changing hardware. Reduce scatter, a 188% improvement. Basically, across the board, we're seeing performance gains from 150 to 200%. These are no small optimizations. These are transformational acceleration that directly impacts the end-to-end training time for real workloads. This is what all the complexity, all the low-level work, and all the sleepless nights led to. A system that moves data between accelerators twice as fast, enabling large-scale training to run efficiently from day one. Up until now, we talked about 32 megabyte message sizes, classic large-scale training workloads. But what happens when the messages are smaller? What happens when the communication pattern is more dynamic, more fragmented, or more latency sensitive? To answer that, we ran another experiment on 32 Gaudi devices, focusing purely on all reduce, but this time across a wide range of message sizes, from 1 megabyte all the way to 256. And what you see here is actually extraordinary. Look at the blue bars. Those represent EFA PeerDirect. The green bars represent the baseline, EFA without PeerDirect. Even the smallest message sizes, such as 1 megabyte, 2 megabyte, 4 megabyte, PeerDirect already jumps ahead. And why? Because eliminating host-side copies benefits every single message size, no matter how small. And please notice that after 16 megabyte size, the green bars, they stay put, while the blue bars keep scaling beautifully. And here's what this chart actually shows us. Without EFA Peer Direct, throughput hits a hard ceiling, around 12 GB. That's the CPU bottleneck slowing everything down. But with Peer Direct, the blue bars, that bottleneck disappears. Throughput keeps rising with the message size, reaching up to 1.7 boost at 256 megabytes. So the message is simple. For collective heavy workloads like all reduce, Peer Direct dramatically accelerates the inter-instance communication and unlocks performance we simply could not have reached before. And now that we've seen the communication benchmarks, let's take things a step further and look at an actual model training performance, because at the end of the day, that's what users cares about. For this experiment, we chose a real-world heavy-duty workload, Habana's DeepSpeed BERT 5 billion parameters model, running across 16 DL1 instances, which is a total of 128 Gaudi processors. This model uses 0-2 optimizer, which significantly reduces memory consumption, but it also dramatically increases the amount of collective communication required. So basically, it's the perfect stress test for EFA Peer Direct. If Peer Direct can make a difference anywhere, it's here. Here's the setup we used for the training. And as you can see, I'm not going to go into much details, but this is, as mentioned, a very heavy communication intense configuration. Excellent for testing the feature. And now, let's look at what actually happened. Peer Direct provided a 153% performance improvement purely from unlocking a more efficient data path. Same hardware, same model, same configuration. The only thing that changed is how intelligently we moved the data between accelerators. This is where the architecture work truly pays off. Better scaling, better utilization, better training, and ultimately, far lower training cost. And if you ask me, this is an incredibly exciting achievement, the kind that reminds you why engineering is worth every late night. So let me share with you the official AWS AI announcement post published when Peer Direct support for Gaudi went live on DL1. They showcased how our joint work enabled multi-instance distributed training to run significantly faster, and how critical this capability was for customers adopting Gaudi on AWS. For me personally, this moment was a milestone. Seeing months of deep technical work, countless late-night debugging cycles, and cross-company collaboration distilled into a public acknowledgement from AWS. It wasn't just an internal win. It became a customer-facing feature that AWS was actually proud to promote. This post also drove a lot of attention from the community, engineers, researchers, and customers, because it marked the point where Gaudi became a truly competitive, scalable, distributed training platform on the cloud. And for anyone who is interested to deep dive into these topics even further, I've attached some useful links, and you can find additional information about the architecture from Intel's and Amazon posts and documentation. And of course, you are more than welcome to reach out to me at any time with any question you'd like. So thank you for your time, and it's been a pleasure sharing this work.
Thank you, Maria, for your presentation. Are there any questions?
Well, I guess not.
Okay, thank you all for listening. Thank you, Maria, for presenting. I will now end this presentation. So
Thank you
thank
so
you.
much for having me. Thank
Goodbye.
you. Bye bye.
Thank you.